Hello there. In this set of notes, we're going to look at how do we recognize, describe, and find domains of functions. But before we jump into functions, I want to talk about real numbers and subsets of these real numbers. All right, so this box just represents the set of all of the real numbers. Okay, and the real numbers are represented by this R with two backs. Well, inside of this set, we have some subsets. All right, so the first two biggest sets that we have within the reals are all of the rationals or irrationals. And then within the rationals, you have the integers, the whole numbers, and the natural numbers. And just to give some examples of those, natural numbers are your numbers like 1, 2, 3, right? These are the numbers that naturally occur. You look down at your hands and you see those numbers. And then the whole numbers are all of the naturals, but also with a 0. So 0, 1, 2, 3. The integers are just all of those, but then also the negatives. So like -1, -2, -3. And then the rationals would be all of those numbers, but all the numbers in between, like 1.5 and -3.8, all those numbers. So yeah, we have the rationals and then the irrationals. And they're all contained inside the real. So let's talk about describing subsets. We can describe using set builder notation. And with this notation, there's some symbols that we have to know. This bar means such that. This little e means is an element of. And these brackets just open and close a set. And within set builder notation, we're going to choose a variable, list the properties of the variable, and tell to which set of numbers the variable belongs. It's not as complicated as it sounds. Let's describe x is greater than 8 using set builder notation. You see, mathematicians, they have to be so specific. And just saying x is greater than 8, well, the long way of writing that is to say the set of all x such that x is greater than 8 and x is an element of the real numbers. Because any number that's greater than 8, that's going to be an element of the reals. So the way that we shorten this is we say, okay, cool. It's the set of all x's such that x is greater than 8 and x is contained or is an element of the real numbers. This whole sentence I was able to write just with some symbols. Another way to describe subsets is with interval notation, and this you've seen before. So if I were to describe x is greater than 8, well, those are just the numbers from 8 to infinity, right? And infinity is never included. And here we saw x is greater than, not greater than or equal to. So 8's also not included. There, we just represented all of the numbers greater than 8, right? It goes from 8 all the way to infinity. One note about interval notation, you can't use it in every single situation, and we'll see that here in a second. All right, let's do some examples. We're going to write each set in set builder and interval notation if possible. So here we have the x's that are between 5 and 15. So in set builder, we have the set of all x's such that 5 is less than x less than 15, and x is contained in the real numbers, right? Because it can't be just the integers because, think about there's like 10.5 in there and things like that. And in interval notation, we could just say, okay, that's just between 5 and 15, and since we don't have any equals to, these are not included. So there we did it. Now the next example gets a little bit trickier because here we have 17, 18, 19. So this doesn't include any numbers in between 17 and 18 or 18 and 19, right? So these are just our natural numbers, right? There's no negatives, so it's not all the integers. It's just from 17 all the way off to infinity, but just counting the natural numbers. So here we would say it's the set of x's such that x is greater than or equal to 17, because, right, all these numbers are greater than or equal to 17, and x is not an element of the reals, but just an element of the natural numbers, right? Because we're not counting all the numbers in between, just those natural numbers. And interval notation we can't use here, because interval captures all of the numbers in the reals. It would include all that 17.1, 17.2. So we can't use that. This is the only thing that we can do here. All right, now, here, why don't you try this problem? Go ahead and pause the video and then see if you get it right. All right, well, hopefully you have that x, it's the set of all x's such that x is less than or equal to negative 8, because all these numbers are less than negative 8, and x is contained in the integers, right, because these are the counting numbers just going into the negatives, so that has to be the integers. And again, we can't use interval notation because we're skipping over numbers to bounce to these easy numbers. So that's set builder and interval notation. All right, so now let's actually talk about what these notes are supposed to be about, the functions, right? What is a function? You hear this word all the time. Well, to understand a function, we first have to know what a relation is. So here are the definitions. Take a moment, copy these down, and then we're going to talk about them. All right, so here's what those things mean. Imagine that we have two sets, A and B, and they've got these elements inside of them. Well, a relation is just any rule that just says, okay, this one goes here, and this one goes here, right? It just relates something from the domain to the range, right? Input to the output. Whereas a function, it assigns each element, so these are all my x's, to exactly one element in B. So to be a function, each of these can only go one place. If this element also maps to another element in B, then this would not be a function. That's a big no-no. Now, two different elements can have the same output. That's fine. But as long as each element in A maps to exactly one element in B. One way that people typically test this is the vertical line test. And the reason that this works, remember that your input is X and your output is Y. So it's easier to show you on something that doesn't work. This, if I input an X of, let's say that this X was like 4, right? The input has two outputs, and the vertical line test went through them showing me that. So this fails, not a function. Whereas on the other side there, you could draw a vertical line through any part of this line, and it's never going to hit more than one spot. So yes, this here is a function. And so now let's talk about evaluating functions at a point. All you have to do is plug in the number. If you have f of x equals 4x cubed plus 6x squared plus 3x, and you need to find f of negative 2, well look, the x got replaced with negative 2, so all of these x's get replaced with negative 2. So just plug it in, simplify, f of negative 2 equals negative 14. Now how would we do it for a piecewise function? Here we have g of x equals, piecewise functions are just functions that are combined with the restraints. So it's square root of x plus 1 if the x that you're plugging in is less than or equal to 4. 3x if it's between 4 and 10, and it's just 5 if you get greater than or equal to 10. So f of 6, where does 6 fall? 6 is between 4 and 10. So f of 6 would just be 3 times 6. So f of 6 is equal to 18. And so now f of 10, well, where does 10 fall? 10 is greater than or equal to 10. So f of 10, there's no x here. It just equals 5. All right, the last thing that we're going to talk about is implied domain. Whenever you're looking at the domains of functions, there's really only two things here that we're going to have to look out for. And those rules are we can't divide by 0 and we can't take the square root of a negative. So if I want to define the domain of 3 plus x over x squared minus 6x, I don't even have to worry about the second rule of taking the square root of a negative. There's no roots. But I can't divide by 0. So what I do is I take that denominator and I go, okay, what would cause this to be equal to 0? And you should know from factoring that, because you could factor out an x here, that setting x equal to 0 or x equal to 6 are going to cause me to divide by 0. And you might be used to saying, okay, it's all real numbers, but x not equal to 0 or 6. Well, let's go back to our set builder notation and do this properly. It's the set of all of the x's such that x cannot be equal to 0 or 6, and x is contained in the reals because it's all of the other numbers. these two things say the same thing, but this is a more proper way of writing it. All right, last example. If we had f of x equals 2x over the square root of x minus 9. Well, we know that we cannot take the square root of a negative. So this x minus 9, it needs to be greater than or equal to 0, right? This represents non-negatives. But hold up, we can't have it equal to 0 because then we'd be dividing by 0. So what we're going to do is we're going to write this as, we know x minus 9 needs to be strictly greater than 0. So solve this for x, we get x is greater than 9. So in set builder notation, we have the set of all x's such that x is greater than 9 and x is an element of the real numbers. All right, and that's the end of your notes. Goodbye.